Oh, that's
Okay.
amazing. Why are you legally smiling so hard?
So we're going to talk today about analysis of motion in an accelerating reference frame. So this is new. We've done relative motion before. And when we did relative motion before, what we discovered was that the velocity of A relative to B is the same as the velocity of A relative to C plus the velocity of C relative to B. And this was a relatively straightforward concept. And the picture that we had was that we have some kind of origin B right here. Okay? And then we had some kind of origin C right here. And we have an object A. And so we can draw ourselves a picture so that when I measure the position of A relative to B, and when I measure the position of A relative to C, then I can observe that the triangle right here, the vectors right here, form a triangle in which RCB and RAC are head to tail. And as a result of being head to tail, they automatically vector sum up to RAB. So this equation right here simply reflects this triangle. And if I now take derivatives, then I get the velocity of AB is equal to the velocity of AC plus the velocity of C. And if I take derivatives here, then I get the acceleration. Likewise follows the same pattern. Okay, so this is all good. But now we end up with some interesting surprises. Go to our next slide here. I want you to imagine that I have a boxcar. No children with this boxcar. And in my boxcar, what I'm going to do is I'm going to have some kind of object that's going to fall from the ceiling. Let's make it interesting. We'll make it a frog. It's going to fall down from the ceiling while the boxcar is accelerating forward. It's the acceleration of A. Okay? So as soon as the frog leaps from the ceiling, now gravity takes over, and so the frog is going to fall straight down because the velocity is going to change in the direction straight down. So if I'm an outside observer looking at the frog, here I am, outside observer looking at the frog, what I'm going to see is that the frog falls straight down. And that's perfectly fine. So that the motion of the frog in an inertial reference frame, that is, we're treating the ground as an inertial frame, the motion in the inertial frame is simply going to be straight down, just like that. But now here's where the surprise happens. Alice is sitting here in the inertial frame. Bob is watching this whole thing happen from a safe little corner in the car, in the boxcar over here. He's over in the corner because he's terrified of frogs, it turns out. And as he watches the frog from his boxcar with the acceleration that's being experienced, what he observes is that the frog appears to accelerate in this direction right here. In other words, its path follows a parabola. Why is that? Well, we can actually justify that fairly simply. We can say from the inertial frame, y for the frog is equal to y0 minus 1/2 kt squared. Simple, right? Okay. So this is...
Would all 9th and 11th grade international?
Okay, so as we work. So this is y for the frog, but it's y for the frog relative to our inertial reference frame A, right? And x for the frog relative to A is simply x0. But if we now consider the position for the frog as measured by Bob, then we have to say that x for the, I think we all agree that y for the frog relative to Bob is going to be the same, right? Because the car is only accelerating in the x direction. So y for the frog relative to Bob is equal to, we can do it formally like this, y for the frog relative to A. Wow. Try again. Plus y for A relative to B, and because there is no acceleration in the x direction, that means that this is effectively 0. So we get y. But x for the frog relative to Bob is equal to x for the frog relative to A plus x for A relative to B. And you can see from the diagram right here that the x for B relative to A is going to include an acceleration component. Specifically, it's going to be equal to negative 1/2 at squared. Because we're accelerating with a constant acceleration in this direction, and so xBA is equal to 1/2 at squared, so xAB is going to be negative 1/2 at squared. That means that when I look at the motion of the frog, I'm going to see, when Bob looks at the motion of the frog, he's going to see the frog accelerating towards the back of the boxcar. This causes a huge problem for us with regard to Newton's laws. Because if I do a free body diagram, in the inertial frame, then what I see, well, it should be green, is that there is only one force acting on the frog, which is mg. If I do the free body diagram in Bob's frame, same forces. Right? There are no additional objects that are touching the frog, and yet for in frame A, the inertial frame, then it is true that the sum of forces in the x direction is equal to the mass times the acceleration, meaning 0, and the sum of forces in the y direction is also, mg pulling straight down, is also equal to NA times y. So Newton's first law works. Over here, in the accelerating frame, Newton's first law fails because the sum of forces on the frog in the x direction is 0, which is not equal to the mass of the frog times its acceleration. So Newton's first law fails. And in fact, if we had some additional force acting on the frog, Newton's second law would fail as well. So what are we going to do about this situation? Well, we can do one of two things. The easy thing to do, but not very productive from a problem-solving standpoint, is to simply say, in inertial reference frames, Newton's first law is not going to hold. And we throw up our hands and say, can't do anything. Or, what we can do is try to remedy the situation by doing some clever bookkeeping. And the way that I can remedy the situation is to come back and consider the frog right here as it falls from the ceiling. and observe that the system is accelerating in this direction, and attribute the acceleration of that system to the creation of what we call a fictitious force that is going to pull in the opposite direction of the acceleration. So that if I want to do a free body diagram in the accelerated frame, what I can now do for our frog is have energy pull down the frog like so, and I can have a fictitious force MA that is pulling in the opposite direction of the acceleration of the reference frame. We say this force is fictitious because there is no cause for it. There is no agent that is causing it other than the acceleration of our reference frame. It's simply a bookkeeping artifact, really. But that fictitious force is point opposite acceleration of the frame, and it has a magnitude of an A. And in fact, when Einstein discusses this situation in his book on relativity, he makes the observation that experimentally it is indistinguishable from a gravitational force. And he does this huge thought experiment with a guy trapped in a chest out in outer space, so there are no forces. And the chest has a big iron hook on the outside of it, and a giant comes along and starts pulling on the hook so that it accelerates in this direction. And he observes that the man will experience, in effect, an artificial gravity pulling him towards the back of the chest. So that if he himself will experience falling towards the back of the chest. From an outside frame, you'd say he's standing still, and the chest is moving, accelerating towards him, but he can't tell the difference. And if he were to take a ball in his hand and drop it, then that ball would accelerate towards the back of the chest also. Okay, so how does this actually work out when we do our analyses of problems? Let's complete this thought. So if we add our fictitious force in, now our Newton's law is sum of forces in the x direction is equal to negative ma. That's the acceleration of the frame right here, which is equal to mass times acceleration in the x direction of the frog. So that we observe that the frog experiences an acceleration of negative a consistent with our diagram right here. So that what we have effectively done by adding the fictitious force is provided a low-cost way of seeing what somebody will experience in the accelerated reference frame. Okay? So we preserve Newton's law at the cost of introducing a kind of fiction. So let's see how this can work out in a couple of situations. First of all, let's see here. We're good. So let's do the classic elevator problem. Man is standing in an elevator on a scale. Okay. Man has a mass of m. The elevator accelerates downwards at a. And we want to know, what does the scale read? Well, previously we have solved this by applying Newton's second law and saying that the man accelerates together with the scale. Okay? So if we do that from an inertial frame, then our free body diagram looks like so. The man has mg pulling down, normal force pushing up, and we observe that in that the scale will actually read the normal force, not the true weight of the man in general. And so we can say that the sum of forces is equal to Fn minus mg, and that has to equal negative mk. By cardinal rule, right? Let's make positive the direction of acceleration. So mg minus Fn equals ma. There we go. And so therefore, what the scale reads is equal to mg minus ma. And all that's good. This is the apparent weight of the man. So for just a moment, the man has managed to lose weight. If we come back and do this analysis in the accelerated frame of the elevator, then we're going to end up with the same equation, but for a different reason. Because now my free body diagram looks like this. We're going to have mg pulling down on the man. We're going to have a normal force pushing up from the scale. And we are also going to have a fictitious force, ma, that is pointing opposite the direction of the acceleration with magnitude m times a. And because the man is in the elevator standing there, his acceleration relative to the elevator is 0. So here we apply Newton's second law. Here we're going to apply Newton's first law because we're measuring the man's position in the elevator, and his position literally doesn't change. So that what he sees is that the sum of forces is equal to mg pulling down minus ma pulling up minus Fn. All of that adds to 0. So that Fn is automatically mg minus ma. We get the same equation that we have here. And this is still his apparent weight, but now his apparent weight takes on new meaning. In the accelerating frame, he literally weighs mg minus ma in the accelerated frame. Now, this has significant application, for example, for International Space Station and other things that have artificial gravity. Imagine that you are in a circular space station that is rotating around at a rotational speed of omega and has a radius r. And you can be standing there. Yeah. Question? Yes. And always in the direction opposite the acceleration. So let's imagine that we have this set up like so, and we want to know now what will the person standing on the floor right here experience. Okay. So if we do this from an inertial frame, then we would have to, we would say that the person is going to experience a normal force pushing in this direction. And that normal force has to be equal to the force that causes him to go in a circle, in other words, the centrifugal force, in other words, m times omega squared r. So that we would say that the person experiences an apparent weight of m omega squared r. Okay, that's fine. But if we analyze it in the accelerated frame, we get additional insight. If we look in the accelerated frame, the man has Fn because of contact with the floor, and the acceleration of the reference frame, namely the circle that he's traveling in, is in this direction, AC. And therefore, the man is going to experience a fictitious force, MAC, pointing in the opposite direction of the acceleration. And force AC is omega squared r. And the man standing there now has a sum of forces which adds up to 0 because he's standing on the reference frame. We end up with that same conclusion that the man experiences the normal force of m omega squared r, but we have this additional insight, which is that the acceleration caused by the rotation leads to a fictitious apparent gravitational force pulling him outwards towards the outside. Sometimes this is called a centrifugal force. You've probably heard of that before. So, you go swimming, you come back, and you put your shorts in the little drying machine that they've got, you press the button, you know what I'm talking about? Okay, the water flings to the outside. Why does it fling to the outside? Well, answering that from the inertial reference frame, the water droplets are moving tangential to the circle, and there they go. So they're continuing in their motion as soon as they get to a speed at which they can no longer hang on, they let go and they fling out outwards like that. From the point of view of the accelerated reference frame, they're experiencing a fictitious force that when it overcomes whatever forces of attraction are holding them to the shorts, they are flung outwards and away. Okay. The same kind of thing can be done fairly conveniently to analyze the classic fuzzy dice problem. So you've got some kind of junker mobile, like so, and the guy has fuzzy dice hanging from the bench. And so the question is, what angle would the fuzzy dice make with the vertical? Draw this larger. What angle will the dice make with the vertical? If we analyze this in terms of the accelerated reference frame, it's actually fairly straightforward. We're going to have mg pulling down on the dice. And if the car is accelerating, notice not moving but accelerating in this direction, then the fuzzy dice will experience, relative to the car's reference frame, a fictitious force pointing in the opposite direction of the acceleration. And all of this will be canceled out by the tension. So that we can immediately say that Tx has to equal ma and Ty has to equal mg, because in the reference frame of the car, the fuzzy dice are not moving. And as a result, we can immediately compute theta, or say that tan theta is Ty over Tx. Is that true? No, Tx over Ty. Because notice that our theta is measured here from south. So we're going to have Tx here, Ty. So that, little did you know, but those fuzzy dice are actually an acceleration meter. Specifically, the acceleration of the car is equal to g times tan theta. So you put a little protractor on your fuzzy dice, and you've got yourself an instant acceleration meter for the car. Who knew?
Yes.
Okay.
Yes.
Yes, we're videotaping.
No.
Okay, welcome back. One last problem, and then we'll call it a day. A car zips around a curve at 30 meters per second, maybe about 65 miles an hour. radius 200 meters. What is the minimum value of mu needed to keep the car on the road? Okay, talk to me about how the analysis goes. And I'd like for you to analyze it from the reference frame of the car itself. So let me just start. Here's our curve. Here's our car from the top. So what does the three-body diagram look like from the top?
Friction points left.
Friction points left, exactly. The frictional force is going to have to keep the car on that curve. Well, notice where the car is. If it's traveling along the curve like so, then then the car is going to have to accelerate in this direction in order to go around the curve at constant speed. This is our constant circular motion model.
When you say the friction is like the wheel, right?
Yes.
Yes, I thought that, like in that case, the friction is in the direction of where the car is going.
Because the car is moving with constant speed right here, there's not going to be a whole lot of frictional force in the direction there. It needs just enough force really to overcome any resistive forces like wind resistance in the direction of motion. But in order to move around the curve with constant speed, there has to be an acceleration straight in, and that has to be provided by the frictional force. Okay? Any other forces acting on the car in the accelerated reference frame?
Would there be a fictitious force pointing right?
There it is. Exactly right. And that is going to have a value of MAC. Now, what if we take a back view of the car? I'm looking at the car from the perspective of its cute little red headlights, or taillights.
MG pointing down.
MG down.
And then you would still have an effect force of friction.
Exactly. Equals, and I think we can do this as mv squared over r. Okay. And now, how does our analysis go?
You can set the sum forces up in the x direction, and they would equal to 0. And
Good.
then sum force in the y would also equal to 0.
So what equations pop out of that immediately?
You would get, taking right to be positive, you would get mv squared over r equals f, and then fn equals mg, or mg.
Good. And what can I do with my f there?
Plug in mu fn, which is mu mg, and then cross out m, and cross out, wait, no.
Yeah, I wrote that wrong. This must be fine. Here we go.
Cross out m, and then the lowest possible mu.
And square over RG.
That's it. And there it is. We would get, of course, the same equation if we analyzed it from the inertial reference frame from the outside observer standpoint. The only difference is is that we would have mv squared over r being the sum of forces